Hi again, and welcome to Embedded Systems course, Prototyping with Arduino Uno. In today's topic, you are going to learn how to work with the Arduino Uno's Pulse Width Modulation pins, or PWM. You will use additional functions like analogWrite to control the LED's brightness, the tone function to send electrical pulses of sound frequency to your piezo buzzer, or to a speaker to generate a musical tone. You will also use the map function to instantly compute and convert one range of numerical value to another. At the end of this lecture, you should be able to create your own prototype that plays a musical tone in sync with the light intensity of your LEDs. So, let's begin. The Arduino Uno can send an analog value, also known as pulse width modulation, to a pin. It can be used to light an LED at a varying brightness, generate a musical tone, or drive a motor at various speeds. In your Arduino Uno, the digital pins 3, 5, 6, 9, 10, and 11 can also be used as PWM pins. So basically, pulse width modulation is simply a technique for producing analog values through digital means. The square wave of digital signals that are switched between on and off are used to simulate voltages between 5 volts and 0 volt. This is done by changing the portion of time the signal spends on versus the time the signal spends off. The duration of the on time is called pulse width. So, to get varying analog values, you change or modulate that pulse width. And if you repeat this on-off pattern fast enough, the result is as if the signal is a steady voltage that is between 0 and 5 volts. The question is, how fast is fast enough? The Arduino Uno has a PWM frequency of 490 Hz, except for pins 5 and 6, which has 980 Hz. So what does it mean? A time period is a duration that is the inverse of the PWM frequency. The term frequency is synonymous to clock speed, clock rate, or the number of clock cycles per second. And if we get 1 divided by 490 Hz, it gives us 0.002 seconds or 2 millisecond time period, meaning 2 millisecond time period for each clock cycle in an oscillating clock signal. Thus, you can say 490 clock cycles per second, or simply 490 Hz. In Arduino Uno, we can use the analogWrite function to generate a PWM signal through its PWM pins. A call to analogWrite is on a scale of 0 to 255, such that analogWrite 255 requests a 100% duty cycle, which is always on, or in this case, fixed to 5 volts. The analogWrite 127 gives us 50% duty cycle, which is on half of the time. This is like saying half of 5 volts, which is 2.5 volts. The analogWrite 64 gives us 25% duty cycle, or 1/4 of 5 volts, which is about 1.25 volts. And the analogWrite 0 gives us a 0% duty cycle. This is the same as 0 volt or simply ground. To illustrate this concept, we will be needing the following materials: an LDR, a 10 kilo ohm resistor, a piezo buzzer, 4 LEDs, and 4 220 ohm resistors, your Uno board, and a couple of connecting wires. Let us connect the 4 LEDs in series with the 220 ohm resistors. And then, we'll use the PWM pins 5, 6, 9, and 10 of the Arduino Uno board to control these LEDs. And in my sketch file, I'll configure pins 5, 6, 9, and 10 as output. But note that you do not need to call the pin mode function and set the PWM pin as output before calling the analogWrite function. So in my void loop, I'll call the analogWrite and pass in values of 0, 64, 128, and 255 to pins 5, 6, 9, and 10 respectively. And then, let's upload the program. And as you can see, the brightness of the LEDs is in proportion to the value we passed in to the analogWrite function. Pin 5 has 0% duty cycle, pin 6 has 25% duty cycle, pin 9 has 50% duty cycle, and pin 10 has 100% duty cycle. To illustrate it further, I'll go back to my sketch file and modify this code. I'll use a for loop and loop through the values of I from 0 to 255, where I is incremented by 5 for each loop. I'll use a delay of 5 milliseconds as well. This code should have a glowing effect on the LED, increasing its brightness by 5 every 5 milliseconds. And then, I'll copy this code and change the starting value of I to 255 until it reaches 0. Then, I should be decremented by 5 for each loop. This should have a fading effect on the LED's brightness. Let's upload the code and check it again. And there you have it. If you want, let's make it a bit slower. I'll change the increment and decrement values of this I variable and set it to just I++ and I-. Let's upload the code one more time. And there you have it, a smooth, glowing, and fading LEDs. And now, let us incorporate an analog input as well. I'll implement an LDR circuit we've used in the previous lecture. If you haven't watched it yet, please do so. This is a voltage divider circuit of two resistances, one from the LDR and the other from a 10 kilo ohm resistor. I'll use analog A0 to read the output voltage of the circuit. And in my sketch, I'll comment this code first, and then I'll declare two integer variables, LDR and LED value. I'll call the analog read function to read the data from analog pin A0 and store it to my LDR variable. What I want to do now is to adjust the brightness of the LEDs in proportion to the amount of light the LDR is receiving. It is like saying, as the environment goes dark, the output LEDs also get dimmer. And when the environment is well lighted, the brightness of the output LEDs also increase. While we can do some simple math computation here to have that behavior, I'll introduce the use of map function. If you recall in the previous lecture, analog read returns a range of integer values from 0 to 1023. This is a 10-bit resolution analog to digital converter. However, the analogWrite function only uses a scale of 0 to 255 integer values. It is like an 8-bit resolution only. So, to properly map any value from 0 to 1023 to a new value ranging only from 0 to 255, we can use the map function for this. So in here, I'll use the LED value variable to store the new value computed using the map function. I'll pass in 5 arguments. The first is the input value to be mapped. I'll use the LDR value received from the analog function, then followed by 0 and 1023. These are the from values, and then 0 and 255. These are the to or the target values. And then, using the analogWrite function, I'll send this LED value to each PWM pin. Let's upload the code and see what happens. As you can see, as I cover this LDR, the brightness of the output LEDs also decrease proportionally. And it glows again when the LDR receives enough light intensity. This simple concept is commonly used in many embedded systems applications. The smartphone that you are probably holding right now has this kind of behavior. The screen adaptive brightness functionality, wherein the screen's brightness adapts to its environment's lighting condition. We can also verify how this map function works by checking the returned values through the serial monitor. I'll print LDR reading, colon, and then display the actual analog read value of the LDR variable. And then I'll print map LED value, colon, and display the converted value. I'll upload the code and open the serial monitor. And from here, you can see the actual mapping on how a number from 0 to 1023 is mapped to a new value ranging only from 0 to 255. Now, let us discuss another function in Arduino that uses the same PWM pins to send a square wave or 50% duty cycle of the specified frequency to be able to produce a musical tone. I'll comment out this code first and type this code, tone, and then pass in 3 arguments. The first is the pin number on which to generate the tone. The second is the frequency of the tone in hertz. And the third is an optional duration in milliseconds. Some reminders though. Only one tone can be generated at a time. The use of the tone function will interfere with PWM output on pin 3 and pin 11, and it is not possible to generate tones lower than 31 Hz. So in my sample code, I'll send a frequency of 660 Hz for 100 milliseconds to pin 5. For you to see the effect of this 100 millisecond duration, I'll put a 150 millisecond delay after it. One important thing to remember, the tone duration is not affected by the delay function. So this code simply means play a tone of 660 Hz for 100 milliseconds and no tone for 50 milliseconds before it loops back and play the tone again. We get the 50 millisecond no tone by subtracting the 100 millisecond duration to the 150 millisecond delay. Let's upload this code and see its effect on our circuit by which pin 5 is still connected to an LED. Well, there's nothing much to see here except from a fast blinking LED. Let me adjust the delay and make it 300 milliseconds. I'll upload it again and check the result. And as you notice, the delay gets longer, thus you see a much slower blinking LED. But take note, I did not create a blinking code. It is the tone function that produces a square wave or a fixed 50% duty cycle for its PWM. And now, for you not just to see the effect but to hear it, I'll remove this LED at pin 5 and replace it with a piezo buzzer. It has a positive and a negative terminal as well. Inside this piezo buzzer is a coil of wire and a small magnet. When current flows through the coil, it becomes magnetized and pulls toward the magnet, creating a tiny click. When you do this hundreds or thousands of times per second, you create tones. And now, you hear a beeping sound generated by your piezo buzzer at 660 Hz. The higher the frequency, the higher the tone. The frequency value should be from 31 Hz up to 65,535 Hz. If you are musically inclined or perhaps you have some background in playing musical instruments, then you can easily use this pattern to compose a musical tone, like a ringtone of your phone. I'll copy-paste this code and modify the frequency and the delay values so that it plays different notes with different duration of pause for each tone. Let's upload the code and observe what happens. Now, does that sound familiar to you? Yep, it's my favorite old-school Super Mario. Let me put some additional tones here to complete just the first part of this. And now, I'll upload it again, and I'm excited to hear this one. And there you have it, the first part of the classic Super Mario musical tone that keeps on looping. One thing you might have noticed here, this code is hard to read and not scalable when we want to compose a much longer version of this music. For that, I'll modify this program and start organizing the list of frequencies and the list of duration for each tone. I'll declare an array of integers called frequencies. In C language, array is denoted by a square bracket after the variable name. Java has adopted this syntax, but C# did not. And then, I'll list down all the sequence of frequencies here, separated by commas. Similarly, I'll declare an array of durations, which will correspond to the delay value that we used. I'll list all the delay values here. And now, I can simply delete all the duplicate codes here and retain just this one pair of tone and delay function call. I'll enclose this code inside a for loop. I'll start a value of I at 0 until I reaches the size of the array. If you are very familiar with the .length property used in Java and C#, well, it doesn't work here in C. To get the array's length, we use the size of operator to get the total amount of memory allocated to that variable. So it means, if we want to get how many number of elements are there in an array, we have to divide it by the memory allocated for each cell. With that, I'll again use the size of operator and get the memory allocated in each cell, which is of type integer. And then, all I have to do is to replace this fixed frequency value with the frequencies variable, accessing each frequency at index I. Similarly, I'll use this durations array to access each delay value pointed by index I. Let's upload the code and hear it again if it sounds the same. Just to clarify a thing, the frequency parameter only holds unsigned integers and the delay function accepts an unsigned long parameter. So I'll just change these two array declarations to unsigned int and unsigned long. And now, to make it more interesting, I will simultaneously trigger the on and off of the remaining LEDs in tune with the tone's duration. To do that, I'll use the analogWrite function just after the tone function call, though I can also use the digital write function here. I'll send a value of 255 or 5 volts to pins 6, 9, and 10. And then, I'll use the tone duration as a delay to the LEDs as we turn it on. And then I'll copy-paste this code and turn off all the LEDs as the tone duration ends. And finally, to apply the remaining time delay before it loops back and play the next tone, I'll simply subtract these duration values with 100 milliseconds. Let's upload the code and see what happens. And as you can observe, you have a Super Mario musical tone with synchronous blinking light. However, if you are not satisfied with the volume of your piezo buzzer, you can try and test it using your computer speaker. What I have here is a portable Bluetooth speaker with 3.5mm TRS audio jack. I'll move the ground from this piezo buzzer and place it somewhere here. Also the PWM pin 5 of the Arduino Uno. I'll put it in one of the vacant space here. In your 3.5mm TRS audio jack, this is the ground, and the middle is the right channel, and the tip is the left channel of your speaker. So, what I'm going to do is to connect this ground of the TRS jack to the ground of the board, and the pin 5 of the board to the tip of this TRS jack. And as simple as that, we have amplified our Super Mario tone. Just a reminder when doing this, please refrain from touching the metal parts of your audio jack while your speaker is on to avoid any possible damage. And so for your code and circuit connection challenge, I want you to implement a similar circuit consisting of 3 LEDs, a piezo buzzer, and an LDR. Try to create a program that plays your favorite musical tone. You can download or copy the equivalent frequency or tone from the internet and embed it in your code. There are thousands of it available online. Or if you know how to play any musical instruments like a guitar or piano, you can compose one yourself. You can use this note to frequency converter as a guide on what frequency to use for each corresponding note that you want to use. So for example, in this demo that I'm going to show you, it plays the notes E, 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 G, C, D, E, F, 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 E, 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 G, G, F, D, C. So I have used this note to frequency converter to replace each note to produce this. Now, using what you have learned on how to use the analogRead, map, and analogWrite functions, I want you to adjust the tempo of the music depending on the environment's lighting condition. The tempo goes fast when it's dark, and it goes slow when it gets brighter. In addition, instead of just an on and off blinking LEDs, try to make the LEDs glow and fade in synchronous with the tone's duration. And again, thank you very much for watching. If you learned something of value here, please click the like and subscribe button for more programming and circuit tutorials. This is Joe Edgo and hope to see you in the next video lecture.